iteration, we try to compute the covariance matrix. So when computing the covariance matrix, we should actually do this based on the new mean. But since we, these samples are not the actual samples, these are the samples from the previous distribution, we compute the covariance using the previous mean. I mean, this is part of the algorithm. And after obtaining the covariance, we also update our mean by simply taking the mean of these new individuals, and this is how your new population looks like. So your covariance changed and your mean also got updated, and this will just continue at every iteration. And things look like this. So the covariance actually becomes pretty big due to the nature of the algorithm, but eventually it is able to cover a large area and be able to converge to something that looks like this. It converges pretty cleanly in this environment, but if you actually look at this, it also looks quite funny because always, even after convergence, the covariance will be a bit large, and the individuals which will be surviving actually will live in this local maxima. But eventually, after sufficient amount of iteration, it converges. And the name of this algorithm is CMAES, Covariance Matrix Adaptation Evolutionary Strategy, which is pretty straightforward. It's an evolutionary strategy, and you maintain covariance matrix, and you adapt covariance matrix at every iteration. So CMAES, which is one of the most popular algorithms in evolutionary strategies. Okay, and let us look at like one more important evolutionary strategy, which is this natural evolutionary strategy from this paper. The weakness of the algorithms we discussed so far is that they discard the majority of the solutions and only keep the best solutions. In the simple case, we only chose the best one and discarded all the other. In genetic algorithms, yes, we also kind of survive only like 10%, 25% of the individuals and killed everything else. In CMAES, similarly, we only chose like 25% best individuals and ignore everything else. However, the weak solutions contain information about what things not to do. And this is valuable. This is very valuable to calculate a better estimate for the next generation. So this natural evolutionary strategy tries to take advantage of the entire population in order to obtain, in order to update, or in order to optimize. So let us look at this fitness score. So as mentioned, this fitness score is nothing but an expectation of a particular function. And if we enumerate this further, enumerate this expectation further, we can actually formulate it this way, and we need to just summarize do the integral over every z value, where z value is xy in this particular case, which is a set of parameters. So we are essentially going over all possible set of parameters and compute their fitness and then compute the integral, and there is the probability of each set of parameters being selected in this particular formulation. And you probably will say that this looks quite similar to something you have seen in the past, right? Where have we seen something similar to this one? Any suggestion? I mean, I intentionally made this look similar. Have you not seen something like this in the past? No idea? Yeah, so this is similar to the reward evaluation function, I mean, which we talked about when we was doing policy gradient. So this was the slide. I mean, this is the slide from the policy gradient. I didn't change anything. So here, we also made this expected reward as our objective function. And then we said that, okay, I can actually enumerate this part like this. And then I was performing some kind of, the enumeration trick. And then I said that I want to compute the gradient over this. Here, we are not saying that we want to compute the gradient. We are not yet saying that we want to compute the gradient. But this and this actually becomes quite similar. So noting the similarity between this one and this one, let us continue our conversation. Okay, so this is what we enumerated, which is a pretty generic thing. And let us look at what we really mean by this equation. So we are optimizing over theta, the parameters of the probability distribution function. Okay, now this became interesting because previously when we were doing the reinforce, the parameter theta was the parameter that was governing the policy function. Here, theta is not something that governs the policy function. It is the parameter that governs certain distribution. And out of each distribution, based on theta, you will be sampling z, which is a solution vector sampled from this distribution. And the distribution was represented in terms of pi. So if pi is Gaussian, yeah, there will be mean and variance. And mean and variance is everything. I mean, is essentially theta. And out of such mean and variance, you'll be sampling z. And z is a solution vector and is xy in 2D case. In policy learning, xy will be a set of parameters governing the policy, which means like neural network parameters. So things are different. In reinforce, we were talking about optimizing parameters which directly govern the policy. Here, sorry for confusion, but here we are talking about optimizing theta, which is not directly the parameters governing the policy. Theta is governing the distribution, is governing the population that generates policy. So this is more like a meta policy in some sense. And we want to optimize so that our meta policy, which is like a population, becomes ideal, becomes optimal, so that if we sample from the distribution, we'll always obtain the better policy. And similar to this reinforced policy gradient, we can just try to compute the gradient out of it. But the meaning of what we are doing is totally different in policy gradient and this natural evolutionary strategy. So I'm almost toward the end of the slide, but I think I'm running out of time. So I will kind of try to stop here. We have 1 more minute. We'll come back to this, but any last minute question? And I mean, if I show you, yeah, it works well. Yeah. If I show you how it behaves, yeah, it works well. So we will come back to this. This is a different way of optimizing your parameters for your policy using evolutionary strategies. And if there is no question, I'll call it a day. If you do come up with a question regarding programming assignment number 1, number 2, yeah, post it on AdStem so that Jong can interact with you. If you have other questions, yeah, please, you can email me, post it on AdStem, and I'll try my best. Okay, thank you everyone, and I'll see you on Thursday. Bye.